Hi, UNI-T just sent in a couple of oscilloscopes for me to take a look. And what I have here on the workbench today is a UNI-T MSO2304X touchscreen operated mixed signal oscilloscope. It has 4 channels, 300 MHz analog bandwidth, and an impressive 5 gig samples per second maximum sampling rate. The 2304X is the highest spec scope in the MSO2000X series for the time being. In this series, you also have the MSO2104X, which has 100 MHz bandwidth, and the MSO2204X, which has 200 MHz bandwidth. UNI-T also sent me one of their MSO3000X series scope, which I will show you in a later episode. So be sure to subscribe to the channel and turn on your notification so you don't miss that video when it comes out in a few weeks. In today's video though, we will concentrate on the cool features of this MSO2000X series scope, and I'm also planning to do a teardown of this scope in the next video. So lots of cool stuff coming, be sure to stay tuned. Besides the 100 MHz to 300 MHz bandwidth and the 5 gig samples per second sampling rate I just mentioned, the MSO2000X series also has 100 MHz memory depth and has up to 2 million waveforms per second waveform capture rate in sequence mode, which are all pretty impressive. UNI-T calls the MSO2000X series a 9-in-1 device in its marketing material, and that's because besides being a digital oscilloscope, it also has tons of additional capabilities. For instance, it has built-in support for a 16-channel logic analyzer. Now, the catch here is that you do need to purchase the UTM-15 logic pod in order to use the logic analyzer feature, as this is an accessory, it's not included as part of the oscilloscope package. The MSO2000X series also has fairly comprehensive FFT capabilities, allowing you to use this scope as a rudimentary spectral analyzer. Also, it has a built-in 2-channel 250 megasamples per second 16-bit arbitrary waveform generator, which supports output frequencies up to 50 MHz. It can also do power analysis, which is useful for people working with switching power supplies. Of course, the MSO2000X also has built-in high-resolution digital voltmeter and hardware frequency counter, which to be honest most digital oscilloscopes do nowadays, and I probably wouldn't characterize these as separate features. But nevertheless, the UNI-T scope is capable of doing this as well. It also has a Bode plot analyzer built in, which you can use to do analysis of the frequency response of the system under test. And finally, it also supports protocol decoding. Out of the box, it can decode UART, I2C, and SPI protocols for free. The protocol analyzer is capable of decoding more exotic industry standard protocols, but you will have to pay additional fee to enable the other protocols. For instance, if you need CAN bus decoding, you will have to pay as an extra option. You do get a trial period for the other protocols if you are interested. So those are the 9 functionalities UNI-T is referring to. Of course, I won't be able to cover everything in detail in a single video. So if there's anything you wanted to see but I didn't cover, please let me know in the comment section below, and if there's enough interest, I may do a separate video on that. Before I power on the scope, let's actually take a look at the exterior first. The MSO2000X series sports a 10.1-inch touchscreen, which is quite large. Just to put the size into perspective, here I have a UNI-T UP01204, and you can see the MSO2304 is much larger than the UNI-T UP01204. And by the way, the 1204 has a 7-inch LCD. The front panel layout is fairly clean and the design is very conventional. Here are the 4 input channels, and these are your standard BNCs. There's no probe interface for power and automatic attenuation detection. Towards the left, we have 2 additional BNCs, and these are for the arbitrary waveform generator outputs. And here we have a socket for the UTM-15 logic pod, which is for the 16 digital input channels. As mentioned earlier, the pod is sold as an option, so you will have to purchase separately if you need the logic analyzer functionality. And let me open up the flap, you can see the connector inside. And by the look of it, it's a proprietary connector. On the back, we have more ports. Here you have an external triggering BNC input, and auxiliary output, which you can use to observe the trigger output, and you also have a 10 MHz clock reference board that can be configured as either input or output, which is going to be useful in a lab setting, as all the clocks can be synchronized to a single source. In my lab, I have a rubidium frequency standard, and it can be used to drive all the instruments back there on the shelf. So I can daisy chain the clock signal to this oscilloscope as well if I want to. On the right side here, we have a couple more of these USB ports, and by the way, you can use a mouse to interact with the UI if you want to, which can come in handy if you have clumsy fingers or just don't like the idea of touching the screen. Here you have an HDMI output port which you can use to drive an external display. The display resolution, by the way, is 1280 by 800. Here we also have an Ethernet jack and also a USB 3 host port. There are multiple ways for you to control this scope remotely. You can either use the Ethernet or using the USB 3 host port to connect to your PC. The MSO2304X series also has built-in web server, so you can use your browser to control the scope interface, which makes it extremely useful. Anyway, I know you guys are probably all dying for me to power this thing up, so let's actually do that. Now, there is a physical button at the back, and once that is turned on, the unit enters the standby mode, and the front panel button is just a soft power button. Alright, let me power it on. The fan in this MSO2304X is a little bit high-pitched, but for a powerful device like this, cooling fan is definitely needed. A modern oscilloscope like this one also takes time to boot up. It has to initialize the software and does a bunch of self-diagnostics. As long as the boot up time is reasonable, I don't think there's much to worry about. And the boot up time is actually pretty fast. It probably took just around 20 seconds, maybe a little bit longer, give or take. I did not really time it, but that's the time it felt like. Of course, we still have this screen protector on, and the screen protector is actually not meant to be on during operation. As you can see, it has some pattern on it, and you can't really see the screen clearly through the film. So let me actually remove it first. As mentioned earlier, this scope is touchscreen operated, and the touchscreen is actually very intuitive. You can see I can move the trace up and down, and you can pretty much control everything using the touchscreen. Actually, you know what? Because the scope has a built-in function generator, I'm going to use it to generate a test signal, so we'll have something to look at on the screen here. So let me do that. First, let's connect the function generator output to channel 1, and let's go to the generator. And let's see here. So we have a 1 kHz signal, sinusoidal, 100 millivolts. Let's just leave it as default. Let's turn it on. And now we have the signal here, so let's press auto set. And you can see now we have the signal captured on the screen here. And like I just mentioned, the touchscreen is actually very easy and very intuitive to use. For example, we can drag it around, and you can see that the waveform moves around with your finger. And if I want to change the vertical scale, I can simply just pinch and spread the screen here. You can see that is very easy as well. Of course, I can also do the same thing with the horizontal. You can see that. So very intuitive indeed. Given the large screen size, using the touchscreen is actually quite enjoyable. Some of the aspects can be controlled via either the touchscreen or the physical buttons and knobs, but a lot of functionality can only be controlled via the touchscreen interface. Or if you have a mouse attached, you can control the screen using a computer mouse. Now let's quickly take a look at the user interface here. So let's first go to the channel, and you can see we have the 4 channels here, and also, by the way, this channel you can see here, we have both 1 MHz and 50 ohm input impedance, so that's actually very useful. And of course, right now the probe is set to 1x, you can change it to 10x, so on and so forth. So that's our channel here, and you can turn it off and on by pressing the corresponding channel menu here. And here is our horizontal. You can see that. We're currently at the scale of 200 microseconds. And here is our acquisition. Here is our trigger. You can see that we have quite a bit of functionality here. And let's take a look at the cursor here. Let's do some measurement. And let's drag it here. And you can see we get roughly 1 kHz. That's not a problem. Of course, we can do the voltage measurement as well. Let's try that. Actually, that's already pretty much set here. So let's come here. And you can see the amplitude here is roughly 100 millivolts. Of course, we can enable both horizontal and vertical cursors. Actually, that's the functionality of a screen. You can see here now we have 1 kHz essentially and 100 millivolts. So that's pretty neat. Let's turn it off. I forgot to mention earlier that the default vertical resolution on the MSO2304X series is actually 8 bits, but the scope is capable of producing up to 12 bits of vertical resolution, and that's what is referred to as ERES, or Enhanced Resolution, in the specifications. Now, because the enhanced resolution is achieved post-acquisition processing, as opposed to through the analog to digital converter, the onboard ADC is actually only 8 bits. obviously the enhanced resolution comes at a cost. So let's actually take a look at that. And to change the setting, that's in the acquisition manual. So you can come here, you can see here, the acquisition mode right now is normal. Of course, we can change it to enhanced resolution. And now you can see we have this enhanced resolution combo box. Let's drop it down. You can see here you can do a 1 additional bit, and you can do 1.5 bit, so on and so forth. And the trade-off here is the available bandwidth that can be achieved. You can see that you can actually achieve an additional 1.5 bits resolution without incurring any bandwidth penalty, but the acquisition speed probably will be impacted. I'm just guessing here, of course. Now I can verify that a little bit later if I remember. Now you can see here with 2 additional bits, you will see the bandwidth now drop to 250 MHz, and with 2.5 bit, it further drops to 80 MHz. With 3 bits, it drops to 31.2 MHz, and with all 4 bits enabled, which is a 12 bits oscilloscope now, the bandwidth is only 12.5 MHz. So the drop-off becomes more drastic as you increase the number of bits of resolution. Definitely there's a trade-off between the vertical resolution and available bandwidth. Higher vertical resolution is useful in situations where signal being observed has high dynamic range. So let's change it back to the default. Before I forget, let's take a look at what accessories are included with the oscilloscope. And here's a box of accessories. Here is our certificate of calibration, and you can see that it was actually done fairly recently. It was done in November this year. And we can see the instruments used for the calibration here. What else? And in here you can see, oh, you can't see here, but inside the box you can see we have 4 of these probes. Now, these are UT-P06, which are rated for 300 MHz. And altogether we have 4 of these. You also have a quick guide and some safety precautions. You also get a BNC to banana clips cable, and also a BNC to BNC cable. And also you have a USB 3 host cable, you can see here, that is used to connect your oscilloscope to your PC. And that's everything that's included with this scope. Alright, I thought I would start with verifying the bandwidth of the MSO2304X. It is specified as a 300 MHz oscilloscope. The 5 gigasamples per second sampling rate is definitely more than sufficient to support this bandwidth. Now, this sampling rate in theory could support up to 1 GHz if the front end of the oscilloscope has sufficient bandwidth. So I'm going to use a couple of different methods to verify the bandwidth. First, I'm feeding in a RF signal from my HP8642B, which is humming back there, to the oscilloscope channel 1. The input impedance of the MSO2000X series can be switched between 1 megaohm and 50 ohms, so it makes impedance matching very easy. So let's first switch the input impedance to 50 ohms, as that's what the RF generator is expecting. To do that, we come to the channel here, and you can see right now it's set to be 1 megaohm. So all we do is just press the 50, and you can see now we're going to the upper route, which is 50 ohm. So that's all set. And now let me enable the RF output. I'm also going to enable some measurements, so we can see the current signal's amplitude and frequency. To do that, let's come here, and we have the frequency counter. Let's turn it on. And also let's come back here, let's see. Of course, we can also add other parameters. Let's come here. And I think we want to do ACRMS full screen. So essentially it's the entire waveform here. So let's do that. Let's actually acquire the signal first. And also you can see right now it's at 121 millivolts. Let's actually change the attenuation a little bit so that we can get roughly 100 millivolts. And the reason I chose 100 millivolts is because we can identify the 3 dB bandwidth more easily. And when we drop to roughly 70.1 millivolts, that's where the 3 dB bandwidth is. So let me right now increase the frequency and let's observe the amplitude. So let's first increase it to, let's say, 100 megahertz. You can see we're at 100 megahertz, no problem. And let's do 200. Right now we're at 200 megahertz, and you can see we only dropped a few millivolts here. And let's just go all the way to 300. Let me expand the scale a little bit. You can see that at 300 megahertz we're still getting roughly 86 millivolts, so it is still above the 3 dB cutoff. Let me enable the second channel to see if we have any impact on the waveform here. And it doesn't seem like there's much. The waveform amplitude didn't really change. And let's actually enable 3 and 4, and you can see that they don't have any impact to the waveform here. The manual didn't specifically say whether the 5 gig samples per second sampling rate is only when a single channel is enabled. But you can see here when we enable channel 2, the sampling rate dropped to 2.5 gig samples per second. And if I disable it, you can see it is now at 5 gig samples per second. And if I enable channel 3 and channel 4, you can see that only when we enable two channels, 3 and 4, or 1 and 2, we have this sampling rate dropped by half. Whereas if I just enable channel 1 and channel 3, the sampling rate remains at 5 gig samples per second. So this behavior tells us there are actually two independent ADCs inside. One is for channel 1 and 2, and the other one is for channel 3 and 4. And this arrangement is quite common among all the 4-channel scopes. Alright, let me keep increasing the frequency and see when we get that 3 dB drop-off. And right now we're at almost 400 megahertz now. And right now we're at 400 megahertz. At 400 megahertz, we just dropped below the 3 dB line. So let's actually drop the frequency a little bit. Let's do 390. Yeah, so you can see that really the 3 dB bandwidth is around 395 megahertz, which is right now what we're showing here. So right now we're at 398 megahertz. You can see we're just around that 3 dB line. So for a single channel operation, actually the bandwidth measured here is at around 400 megahertz. Now let me enable both channel 1 and channel 2. And you can see there's not any visible degradation of the signal. So it appears we actually have quite a bit headroom to go. So let's keep increasing the frequency here. And right now we're at 500 megahertz, and you can see that the hardware counter actually measured frequency with no problem, 500 megahertz. Of course, the amplitude dropped further down, but we are able to still measure the waveform with no problem. Let me change the amplitude a little bit, and let's keep increasing the frequency. .600 megahertz. .700 megahertz. .800 megahertz. Of course, right now the amplitude had dropped significantly, but you can see that we're still able to measure the frequency here at 800 megahertz, and also the waveform remains reasonably clean. So let's do 900. And right now we're at 900 megahertz. Let's actually change the scale a little bit. I'm actually pretty impressed. Right now you can see we're at 900 megahertz and the waveform remains very clean. Let's keep increasing. Let's actually change the amplitude here. Let's change it to 1 gigahertz. You can see that right now we're at 1 gigahertz and the captured waveform remains very stable. And now if I enable channel 2, I would expect the waveform to degrade even further, because right now we're at 1 GHz and we only have 5 samples per waveform. And if I enable channel 2, it would be 2.5 samples per waveform. Yeah, you can see that indeed the waveform becomes a little bit fuzzier, and that's to be expected. And I played with it a little bit. It seems that the maximum frequency it can actually capture is right around 1.1 GHz. So let me show you that. So let's increase to 1.1 GHz. You can see that we're still able to measure the frequency here, 1.1. And if I increase it further, obviously you can see that the measured frequency is actually quite a bit off now. Right now we're at 1.14 GHz according to the HP8642B, but right now we're measuring 1.13. So it appears the frequency counter, the limit is really at 1.1 GHz. And of course at 1.1 GHz, if I enable channel 2, you can see that the waveform had degraded significantly. And I just want to show you what is on the HP8642B. You can see that the current output from the HP8642B is 1.1 GHz. And what we have here also on the screen is 1.1 GHz. I am actually quite impressed by the bandwidth of this oscilloscope. For sinusoidal signals, you can push well beyond the specified bandwidth. Although the amplitude becomes uncalibrated, you can still do a lot of useful measurements. And by the way, the maximum vertical sensitivity on this scope is rated at 500 microvolts per division. So let's actually take a look at the noise level at that sensitivity. For that, I'm going to go to the channel, and I'm going to actually ground it first. So let's ground it. And now channel 1 is grounded, and I'm going to increase the scale here. So right now we're at 500 microvolts per division. And let's enable the cursor. Let's do voltage. And actually, let's go back to cursor. We apply it to channel 1. So the noise level is roughly at 1 division here. Let's see if we change channel 1 to 50 ohm. Does it change the noise level? Yeah, the noise level goes down a little bit. Okay, so that noise level was actually at 1 meg ohm. And with or without input, it looks similar. Yeah. So at 50 ohm, you can see the noise level is actually lower. It's at roughly 420 microvolts. One thing I really like about this scope is you have this default button, and you can restore everything to the factory default by just pressing this button. Of course, you can see that it's a little bit recessed, so you don't actually hit that by accident. Of course, let's try that. So we wanted to reset to default, and you can see that now everything is set to default. And this is useful if you had to play it around and you don't know what settings you had changed, and you just want to restore everything to the factory default. Anyway, we can also independently verify the bandwidth of an oscilloscope using an Avalanche pulse generator, which can generate pulses with very sharp rising edge. The rise time is typically in the lower hundreds of picoseconds range, so by measuring the rising time of these Avalanche pulses, we can infer the front-end bandwidth. This method is capable of verifying the bandwidth of oscilloscopes well into the gigahertz range. So now let me set it up. And here is my Avalanche pulse generator. You have seen me using this in a lot of videos. And let me hook it up to channel 1. And I'll power it on. Of course, right now you can see we have these pulses here. And let me actually just auto-acquire it. Of course, we have to do some adjustment here. So let's bring it down. And I'm going to expand it. And you can see here is the captured Avalanche pulse. And let's see what the rise time is. So I'm going to choose the automatic measurement. And let's do add. think it's going to be horizontal. And here we go, rise time. So let's hit OK. The captured avalanche pulse is very, very clean. If you look at the automatically calculated rise time here, it's right around 1.25, 1.26 nanoseconds. This actually put it just slightly under 300 MHz. And let's take a look at the measurement ourselves. So I'm going to enable the cursor. And let's do roughly 10% to 90%. We're getting about 1.18 nanoseconds. So you can see that for all intents and purposes, this is a 300 MHz scope. The memory depth of the scope is up to 100 megapoints per channel, so you can store a lot of waveforms. Now, once the waveforms are captured, navigating through them becomes the next challenge. With the MSO2304X series, you can actually navigate through the captured waveforms based on the criteria defined. And let me actually demonstrate this. Let me first stop the capture, and let's actually see how many we captured. It looks like we only captured one. Let's start again. Let's see how many. So let's actually increase the memory depth a little bit. Let's run, and let's come to acquisition. So the memory depth, let's change it to 250K. Let's run again. Stop. And we captured 2. Okay, let's run. Stop. We captured a few. Let's actually increase the memory depth even more, as I do want to capture a few more. So let's do, let's say, 5 megapoints. And let's hit run again. So now we should have a lot more. Let's just see. Yep, we have quite a few here. So what I'm going to do here is to search the next captured pulse. And to do that, I click on this magnifying glass. You can see here, search type is edge, and I want to search the rising edge. Everything I will leave as default. So let's turn it on. And you can see we find this. Now we can even go to the event table. You can see now we can essentially go through the different captured pulses here. So let's zoom it in. So you can see here in this table we have all these different timestamps and the different pulses captured. So if I double click on one of these, you can see here 128.4 microseconds. And you can see that we navigated to that pulse. So this makes searching these kind of short pulses very easy. And we can find another pulse here. Let's go to the last one. And you can see we find that pulse with no problem. Now, one of the challenges of capturing this sparsely occurring signal is that once the scope is triggered, it will continue to sample the channel until the sample memory has been filled. The problem is the signal of interest could be very short, and the repetition interval could be very long. So if you're doing a single shot, you are probably not going to capture many instances of the signal of interest, even with a large sample memory. And this is actually what is happening here. You can see that if I just close this, we have this very short signal here. And if I zoom out, you will see we are actually not capturing that many signals here. You can see that the sample memory essentially is wasted, as for the majority of the time we're just waiting, there's nothing happening. And we do capture the signal here and there. So can we do better? The answer is yes. To solve this problem, many modern digital scopes have the segmented memory mode. The concept of segmented memory is fairly easy to understand. By dividing the sample memory into smaller segments, when triggered, the oscilloscope will fill the next available memory segment, and once the segment is filled, the oscilloscope will stop capturing data and rearm the trigger and wait for the next trigger event to occur. So even if the trigger events are few and far in between, like what we have seen here, you are guaranteed to capture all these rare events. And because each memory segment is operating essentially independently, you are not going to waste all this space, because once a memory segment is filled, the capture is stopped. Let me demonstrate the segmented memory mode with the MSO2304X. Now, I think the user manual is a little bit confusing on this feature, as it mentioned the segmented memory mode under the acquisition mode, and it called it sequential acquisition. The problem is that if you take a look at the acquisition mode, you will see that none of the acquisition mode is called sequential acquisition. So how do we enable it? As it turned out, segmented memory mode is actually enabled by the record function. So let me show you that. Before I do that, let's actually get rid of the search. And let's actually make sure we can get a single stable trigger. So to enable recording, you have to come here to the menu, and you can see we have this record button, and that essentially is the segmented memory. So we come here, we can define how many frames. Let's just say we want to capture 1000 frames. And by the way, another area it's not very intuitive is if you press on the frame, you can see the number is highlighted. Of course, you can use this multifunction knob to change the number here, but that's quite slow. So how do I enable the keypad? Well, as it turns out, you have to double click on the number here. So now, for example, if I wanted to say enter 1000 and enter, now we're going to capture 1000 frames. And now all we need to do is press the record button. And you can see, right now we have already captured 1000 frames. To cycle through these captured frames, you can move it. Let's move it here, and we can use the play button here. You can see we're playing through the 1000 frames. Of course, we can stop anywhere we want. Also, you can use this to drag around and go to the specific frame you're looking at. You can see here. Of course, we can go to the last frame, and we can go to the first frame, and we can play. Now, I do wish I could cycle through these captured segments via the multifunctional knob, or using these arrow keys to go frame by frame, but you can see that they don't work. And the only way to navigate through these captured waveforms is to use the touchscreen here. You can see that. So this is definitely not as convenient. And let's see if we can actually hide this waveform recording dialog and still navigate through the waveforms here. Now you can see that you can use the knob or these arrow keys to navigate the captured frames. The only way you can do that is through that dialog box. The problem here is now you are blocking the view. Of course, you can always put it on the side, but it's a little bit clumsy here. You can see that we can navigate through like this, but the dialog box is on the screen here. Nevertheless, you can just see how useful segmented memory is. In this case, we're able to capture 1000 frames of the Avalanche pulses. And according to the manual, the maximum number of the segments is at 200,000, which is more than enough for most of the use cases. The auxiliary output BNC on the MSO2304X series can be configured as trigger output. So let's actually double check what it's currently configured as. To do that, I'm going to go to the utility menu, and let's see the rear panel here. You can see that currently the auxiliary output is configured as trigger output. So that's actually what we want. Let's keep that setting here. In the specifications, it mentioned that the waveform capture rate is up to 500,000 waveforms per second, and in sequential mode is even higher, up to 2 million waveforms per second. Keep in mind that the trigger rate is not the same as the update rate, but they are related. Of course, the triggering rate is also dependent on many other factors, and the memory depth and the display method also affects the triggering rate. So let's actually take a closer look. Now I have connected the auxiliary output from the MSO2304X to the UPO1204. And what is showing on the screen here, you can see that's the trigger waveform. Let me zoom in a little bit. Currently you can see the frequency measured is right around 60 kHz. And of course right now the horizontal is set at 1 nanoseconds per division. So let me change the horizontal on this MSO2304X and see what impacts it has on the triggering rate. So let's reduce it. Oh, you can see actually it's getting faster. Now we're at 367 kHz. And let's see if that's the highest. It appears that the highest we get right now is at 520 kHz. That's with a horizontal of 20 nanoseconds per division. So this 500 kHz number actually matches what the spec says about the refresh rate. Now, as I mentioned earlier, the triggering rate is actually affected by multiple settings. So let's actually take a look here. So if I go to acquisition, for example, right now the acquisition mode is normal. And I mentioned if we change it to, let's say, average, actually this one will lower it. Yep, because we're actually averaging 2 per waveform. And let's change it to enhanced resolution. You can see that right now because we don't have any additional bits, so it didn't impact the triggering rate. So let's actually add 1 bit. And you can see immediately the triggering rate dropped to 88 kHz. Although bandwidth is not impacted, but the waveform update rate is significantly slower. So as I suspected earlier, even though adding 1 bit to the resolution did not impact the bandwidth, but you can see here from the triggering rate, the refresh rate definitely dropped. So let's do 2 bits, and it didn't actually change the update rate here. So let's do 4 bit. And it seems the enhanced resolution actually, it doesn't really matter how many bits you enable, the update rate remains the same. So let's actually disable this. We also know the memory depth also impacts the refresh rate. So let's actually increase the memory depth to 25K. And you can see that immediately we drop down to 120 kHz. And let's increase further, 250K. Yep, dropped even further. And let's go to 100 meg. And right now we're only triggering at 40 some hertz. So let's actually change the horizontal scale down. Yep, you can see with the maximum memory depth, we're only able to trigger at 43 hertz. And I change the acquisition mode to normal. You can see that it seems that we're right around still 45 hertz. So let's change the memory depth back to auto. And now we can see we do have some dead bands. Let's actually stop. And you can see we roughly have, let's see, maybe 7 milliseconds of dead time between the different frames here. Let me resume running. And let's change it to 2 microseconds per division. And let me actually enable the Avalanche pulse. You'll see the triggering pattern will change. And now we are triggered. You can see that the triggering frequency actually changed to about 40 kHz. So that's the triggering signal observed on the oscilloscope. Next, let's briefly take a look at the single shot capability of this oscilloscope. For the testing, I'm having a power supply outputting roughly 3.6 volts, and currently the output is turned off. I'm going to turn on the power supply shortly, but let's actually check out the setting here. Right now, you can see here we're using DC coupling, and everything looks good. And you can see here we are setting the trigger point to be roughly around 400 millivolts, and the trigger position is right here. And let's enable single capture. We can either press a button here, or you can use the mode button to cycle it through. Either way, you get to the single capture mode. So let's enable the power supply output. And you can see we captured the output with no problem. Not sure if you can see it, but we did capture some sort of spike right around this rising waveform here. So we can actually zoom in and take a look. So for that, I'm going to change it here, and I'm going to expand the horizontal here. So you can see some of the spikes on the waveform here when the output is being ramped up. So taking a single shot is very useful to capture the power on characteristics of your power supply. Now let's take a look at the frequency modulated signal with the scope. With the MSO2304X, it's actually kind of convenient as we have the built-in function generator. So let's use the function generator to generate that FM signal here. Let's bring up the function generator. By the way, you can bring it up here, or you can use the menu here. Let's just see. We have the generator, and let's generate a sinusoidal frequency. Let's do 1 megahertz. 1 meg. Let's change the type to FM. For the modulation frequency, let's do 100 hertz. That's fine. The deviation, let's do 200 kilohertz. So we can see it more prominently on the screen here. 200 kilohertz. So now let's enable the output. I'm going to reacquire the signal. And now you can see that is our frequency modulated signal. You can see just how fast the update rate is. Next, let's take a look at an amplitude modulated signal. For that, I'm going to go to the generator here, and let's change it to AM. And for this one, let's see here, modulation frequency, let's do 1 kilohertz. 1 kilohertz. And carrier, 1 MHz is fine. Alright, so let's check it out. And let me adjust the trigger here. You can see that this is our captured amplitude modulated signal. Very nice. Of course, UNI-T designated the scope as ultra phosphor, which means it has intensity grading here. So let's actually take a look. Now, the brightness of this is right now pretty high, so that's why you probably can't see it. So let's come back here to display. And if I change the brightness here, let's do backlight. And you can see the intensity graded signal here. And also you can use the different color schemes as well. So let's go back to display. You can see here, we can turn on the color. And now you can see that this essentially, let's stop this. And this essentially is an amplitude modulated signal using the color display. And let me change it back. Now, AM signals are not the easiest to trigger. To get a stable signal, one trick is you can select the trigger level to be close to the amplitude. So let's actually take a look to see if that works. So I'm going to increase it just at the tippy top here. And you can see that now we get a relatively stable signal. Speaking of triggering, the scope offers extensive triggering options. So let's take a look here. So let me select triggering. Let's zoom in a little bit. You can see that we currently are triggering on edge, but you have different types. You can trigger with a delay, timeout, duration, so on and so forth. And you can also program to trigger on runt signal and also on nth edge. So it's quite comprehensive. Of course, you can trigger on different protocols as well. With this scope, you can also do mathematics with the waveforms captured. And there's a lot you can do with this feature. So let's take a look. And for the mathematical functions, we need 2 inputs. So I'm going to use the other signal generator output as well. So let's hook it up. And let's come here. Let's actually turn off the amplitude modulation. Let's do continuous. So for this one, let's actually generate 2 signals. One is a 1 MHz signal, as what we have here. The other one, let's do a 1 kHz signal, which we have here. So let's enable that. And also I'm going to enable channel 2. Let's do an acquire here. So now these are the 2 signals acquired. Now this is a little bit interesting. I think the outputs from the 2 generators are actually independent because you can see here, this upper one is a 1 MHz signal and the lower one is a 1 kHz signal. In theory, the 1 kHz should be much wider, but right now we are not able to sync up on that signal. So let's adjust the time scale here to see if we can see anything. Yeah, so you can see the 2 signals are not completely in sync. Let's actually change channel 1 to be a little bit lower. Let's see if we see any difference here. Let's do maybe 100 kHz. 100 kHz. Yeah, we still have the same issue. Anyway, not a big deal here. It's interesting to see that the 2 output signals from the signal generator are actually not phase locked. I'm not sure if there's a setting to control that, but I'll have to check the manual later. For now, let's actually enable the mathematical function. You can see that we have the source A and B. Essentially, you can choose 2 out of any of the 4 channels. So let's do source A corresponding to channel 1, source B, let's choose channel number 2. Let's actually multiply these 2 signals together, as that will give us an amplitude modulated signal. So let's do that. A multiplied by B. Let's enable that. So by the way, by default, it is enabled in the same window, but you can also display that in an independent window here. So let's change to that. Of course, right now you can see we're not seeing anything. I suspect that's because the scale is off. So let's zoom it in a little bit. Of course, right now you can't really see what's going on. Let's change the time scale here. Aha! Now you can see we're essentially seeing an amplitude modulated signal. To make it stable, I think we just need to change the trigger source to channel 2. So let's come here to trigger and source. Let's do channel 2. And now you can see the computed waveform is stable. And let's do another one. I'll come back here, and you can see we have essentially 4 sets. I can do the second one. This time just do A plus B. And let's do source B, also channel 2. Let's enable that. And I probably need to adjust the scale again. Yeah. And let's take a look. You can actually do a lot more with the mathematics. So let's actually try another one. Come back here. Let's do math 3. And this one, let's change it to advanced. So the expression we're going to use, I'm going to do the absolute value of this waveform here, which is channel number 2. So let's do that. So edit, let's clear this, and we're going to do, let's see here, the absolute value of channel 2. Okay, and let's see. Yep, that should be good. So let's turn it on. And you can see that now we have the absolute value of channel 2. And of course, you can apply some digital filtering to any of the 4 channels as well. So let's take a quick look here. You can see that you can, for instance, change it to filter, and you can see that you have the ability to apply these filters. Of course, because right now we are just outputting the sinusoidal, so I'm not going to show you the filtering capability here, but you get the idea. Now let me briefly demonstrate the Lissajous figure using XY plot, because we still have the 2 inputs here. Right now, both of the signal generator outputs are set at 1 kHz. So let's actually enable the XY mode. For that, I come here to the horizontal. You can see right now we're displaying YT, and I just change it to XY. So immediately we have this Lissajous figure displayed on the side. And you can see the source of the XY mode can be any of the 2 out of the 4 channels here. Anyway, so right now we're using channel 1 and channel 2. Let's actually adjust the scale a little bit. So let's go to 1. Alright, now let's change the frequency of one of the channels here. So let's do the first one. Let's come here to frequency. So let's change it to 2. And you can see here. Now these 2 signals are not exactly in phase right now, so that's why the Lissajous figure looks a little bit distorted here. And we can change that probably. Let's change the phase. Yeah. So now let's change channel 2. Let's do the frequency here. Let's actually close this. See if we can change the frequency. No, we can't. So let's move to the side here. And I'm going to change the frequency here. We get our Lissajous figure very nicely. And we can come back to the first one. Let's see. And that is the XY mode. And by the way, the scope also has built-in help. Although I had read through the manual, but I forgot how to display the phase angle here. So let's actually take a look at help here and see how do we enable that. So I think it's somewhere down here explaining the display. And yep, it's right here. You can see it says, okay, press the cursor key. So let's do that. So come back here, cursor, and let's do cursor on. Yep. And that's actually displaying the information about this Lissajous figure. And you can see that the phase difference between these 2 signals are 46 degrees. The FFT function on this scope is quite powerful, and you definitely can use it to do some spectral analysis. I have to say though, the implementation only improved slightly over the same function on the UDP-1204 I reviewed a while ago, and it's still pretty buggy. Let me just show you around here. So right now we're observing a 1 kHz square wave, and you can see here we have the FFT enabled. It is showing the peaks here. So let's actually add the label to the display here so we can see what exactly those peaks corresponds to. So I come to the FFT here, and you can see these are the parameters you can play with. Now keep in mind, some of these parameters, I don't know why they won't stick. If I change the end frequency, for example, and then change the FFT points, it will actually change the end frequency as well. And I probably will show you that, but right now I don't want to mess up the display here. So let's go to trace. So for example, right now we're displaying a maximum of 5 peaks. So let's turn on the list. And you can see here, so you can see that we have the frequencies here corresponding to the odd harmonics of the square wave. And of course, if I change the scale here, you will see that we can see the spectrum is changing accordingly as well. So that's all good. But let me show you some of the gotchas. So if I come back here to the FFT, so right now, let's say we want to change something here. Let's go back to general, and we want to change the FFT points. Let's say we change to 32K, and watch what happened here. You can see the end frequency now changed to 38.147K, and although we want it to stay at 10 kHz, so that's what we said before. Now you can see in the background, the display actually was not as sharp as before. So I'm not sure what's going on here, but you can see here the 32K FFT should be sharper than the 16K FFT, but obviously that's not the case here. So anyway, so now if I change the horizontal scale, you can see the sharpness increased. So definitely some bugs in the implementation of the FFT here. Now let's come back here. You can also change the window here. Right now we're using a rectangular window. You can change it to Henning window. You can change it to Hamming window, so on and so forth. So that's all good. But again, let me just show you again. So let's change it to 64K, and you can see that the end frequency automatically changed. Now, I think what it's trying to do is to adjust the frequency optimally to match what the current waveform display is. But I have to say though, that is a little bit annoying because sometimes you do want to make sure the end point is at a set frequency. Let's change it back to, let's say, 10 kHz. And now the display is back to normal. I really hope UNI-T can address some of the inconsistencies I see here, as the FFT function overall is a very good feature and definitely has great potentials. Just like on the UDP-1204, we can also do the waterfall display, and right now you can see we're sweeping between 1 kHz and 2 kHz, and that's the spectrum displayed on the scope here. In this mode, we do have some limitations as well. If I go back to the FFT, you can see here, now we're having 16K points, but if you try to increase it to 32K, for example, you can't do that. The highest you can do with a waterfall display is with 16K points. The MSO2304X series also supports Bode plot, and that's actually a very useful feature. Bode plot gives you the frequency response of the system, and also it can tell you the phase relationship as the frequency changes. So let me demonstrate that with a simple RC low-pass filter. And here's our setup. You can see we have a 1K resistor, and here is a 100 nanofarads capacitor, and this essentially is a very simple low-pass filter. The BNC to banana clips here, that's the signal generator's output, and I connect it to the input of the filter, you can see here. Then I have two oscilloscope probes. One is probing the input, and the other is probing the output. That's how we generate that phase and amplitude relationship. Now let's take a look at the setup on the scope. To enable Bode plot, we come to the menu here, and you can see we have this Bode. And here is the configuration of the Bode plot. You can see that we have the input channel, which is channel 1, and output channel currently is channel 2, and we have already set it up. And the starting frequency is 50 Hz, and the stopping frequency is 10 kHz. And also I had to set the number of points to be 100. Keep in mind that you can actually set it to be higher, but just realize that it will be much slower. Of course, once I enable the plot, it will be plotted onto this pop-up window. Now, the pop-up window itself, you can see through, so that might not be ideal. Let me actually change it right now to, let's say, transparency. I want to change it to 0. And unfortunately, I have to come back here to change it every single time if you want to do that. So let's go back to Bode plot. Now you can no longer see the background here. So let's enable the run. Now we have captured the filter response. You can see here, the cyan line, that's essentially the amplitude. You can see that it rolls off after about 1.5 kHz. And the other line, that is our phase shift between the input and the output. And let's actually take a look at the list here. So let's scroll down to see if we can find the 3 dB mark. And you can see that the measured 3 dB bandwidth is right around 1.7 kHz, and that's for the specific values of the components I used. And here is just a quick demonstration showing you the protocol decoding capability of this MSO2304X. Currently, we're outputting some serial data from the Arduino here, you can see, and the waveform right now is stable. That's because we're actually triggering on the data here. So let me briefly show you the trigger setup. You can see that we're triggering based on RS-232, and we have set up the configuration here. The bitrate is 9600, and we have 8 data bits, so on and so forth. You can see we are actually triggering on data. The data is 72. That corresponds to H. So just to demonstrate if we are triggering on this, you can see if we're changing it to, let's say, 12, I don't think we have anything here, 62 rather, you can see the display becomes unstable. That's because we don't have this data point in the display here. So let's change it to 72, and now we're triggering on the letter H again. So that's on the triggering side. Now let's take a look at the protocol decoding side. So I come here, you can see we have this, let's see where it is. Yeah, decode. You can see here, again, we're setting up as RS-232. And we also have a bit rate of 9600, 8 data bits, and 1 stop bit. So that's the data we're generating from the Arduino. Of course, I can also enable the event list that will show us the decoded symbol here. You can see that. That is our hello world. As I mentioned earlier, out of the box, you can decode UART, I2C, and SPI signals. But if you want to decode CAN bus signals or some other signal types, you'll have to pay for the additional licenses. As I mentioned earlier, you can connect an external monitor to the MSO2304X series via the HDMI port. And that's exactly what I did here. You can see that the display is essentially replicated on that external monitor. Of course, if I change the scale here, you can see that everything is displayed accordingly. And this is very useful in a classroom setting or if you're just trying to demo to a larger audience. Also, you can control the oscilloscope via PC. So this is also very convenient, as you can see here. Now, I have just connected the Ethernet to the MSO2304X. Let's take a look on the computer here. You can see that we can navigate to the IP address here. Now, this would be dynamic, and you have to verify that from the setup here. So let's actually take a look at the setup. Now let me go to utility. By the way, you can navigate to utility either through the menu here, or you can do it from the button on the oscilloscope. So let's go to utility, and you can see here we have LAN setting, and right now the IP address is 10.0.0.68. So that's what I have on the computer here. So anyway, once you navigate to this URL, and you can control the instrument directly from here. So let's do that. And you can see that right now the computer is mirroring what we have on the oscilloscope here. So anyway, so if I change, for example, let's actually zoom out, we can essentially see what is going on the oscilloscope on the computer here. And of course, you can also control the oscilloscope as well from here. So if I go here, you can see that we can essentially bring up different functions here. And that is being reflected both on the external monitor and also on the oscilloscope. So definitely this is a very convenient feature. Let's come to the signal generator here. And let's just change it to a different signal. Let's do noise. And you can see that the change is immediately reflected on the oscilloscope. And of course, we can adjust it. You can either adjust it on the scope, or you can adjust it on the computer here. So let's try this. And let's change it to another waveform here. Let's do pulse. And let's change the scale here. And you get the idea. Alright, that's pretty much all the major features I wanted to show you in this video. Obviously, there's still a lot I haven't shown you yet. If there's anything else you wanted me to show you in another video, please let me know in the comment section below. In the next video, I will do a teardown of this oscilloscope, so please stay tuned. I hope you enjoyed this review video and learned something new. If you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.